we do have to get back to school now, right? Bummer. And furthermore, what we have, y'all, is probably the most important module of the year, okay? Module 8, Stoichiometry. So I'm going to need you to really pay attention today. There are going to be some of the videos that are playing, and you're just going to have to put up with them. I did cut some of them short so that we didn't have to listen to the whole thing. Really kind of the first part of our lecture today is going to be the most important part. And the second part has just a new thing that we're introducing to about empirical formula and stuff like that. All right, so are we ready? You need to turn to page, it's 8A, lab 16. Page, looks like 650 something?
53.
Okay, mine is 55. Y'all's is 53? Okay. All right, so you see you have a bunch of boxes on there. All right, so you're going to be writing some stuff down. Okay, so let's kind of get our minds back kind of out of the snow, right, and back into chemistry to remember where we left off. Okay, where did we leave off? So remember we left off with the mole and how I told you the mole is your friend, right? So don't be afraid of the mole. We're going to use the mole concept. We can calculate and relate the quantity of any substance in a chemical reaction to any other substance. All right, so we can have, how do y'all like algebra? You know when you're having to solve for an unknown? Have you ever had to solve for two unknowns? And that's worse, right? So in chemistry, we could solve for 4 unknowns, and it's not hard. It's not as hard as algebra is, okay? So it actually, just one little bit of information can give you the answer to the rest of your questions. And so that's how powerful this little mole is. All right, so we can then convert to relate the masses because we don't weigh things by mole, we weigh things by gram. And in order to do that, we're going to have to do converting. So the conversion process is the most difficult part of this lab. And keep in mind, it's just converting something. That's all we're doing. It's not more complicated than that. So if you're happy with conversions, I don't like them, but the math is not that hard. Just do the factor label method and we'll be cool. All right, you'll be able to figure it out. So it's kind of like a recipe. As long as you know what you need, you can make the proper recipe. And that recipe is called stoichiometry. So one of the things I like to show for that is this right here. Okay, so what are we looking at? That's a s'more. So if we're going to make, how many s'mores do I have on this slide right here? One s'more. Okay, but I have 2 graham crackers, 1 marshmallow, and 1 square of chocolate. Is this how y'all make your s'mores? You know what, I leave that second graham cracker off. So in other words, so I put the marshmallow between the bottom graham cracker and the chocolate, like that. So the chocolate, because otherwise there's just too much graham cracker and I can't taste my chocolate, right? So I got to have more chocolate. The chocolate's melting, of course, if you do it right. No, it's good, yeah. So, but think of this as stoichiometry. 2 of one thing, 1 of one thing, 1 of another thing. All right, and that's going to be my coefficients. We'll be looking at that, and they'll be telling me how many moles. So if this were a chemical reaction right here, a chemical equation, we would have 2 moles of graham crackers, 1 mole of marshmallow, and 1 mole of chocolate. Get it? Easy breezy. All right, so here's our first example. You need to write this down in that box on your book right here. The problem is that a chemist forms ammonium sulfate by combining ammonia and sulfuric acid, H2SO4. If she ends up making 12.2 moles of ammonium sulfate, how many moles of ammonia were used? So all you need to write down is this equation in there. Don't write down the whole question. You'll put that information in there. So write down NH3 plus H2SO4 yields that thing right there. Okay, so take a look at that thing. NH4, the whole thing is in parentheses with a little 2 subscript right down there. And then we have our SO4 here. So I want to talk about this for a second. If I have the whole thing in parentheses right there, what can you tell me about that little 2 at the bottom outside the parentheses?
Goes to each element.
It's going to apply to both of them. Okay, so the first thing we're going to need to do is balance this equation. And in order to balance the equation, we have to know how many of each thing that we have. So don't forget that on this side I have 2 N and 4 times 2 H right there, okay? All right, so does anybody feel like they want to try to balance that? What? Oh gosh, I already balanced it. I told you on the next line right there. It looks like all we have to do is that. Okay? So what this is telling me, just like my s'more recipe, I have 2 ammonia with 2 moles of ammonia and 1 mole of H2SO4, sulfuric acid, gives me how many moles of the product? 1. Just 1. Now I'm going to relate those to each other. How many moles of NH3 does it take to make 1 mole of NH, this one, the product? It takes 2 to make how many? 1. All right? So that's really all the information you need. Now, I've given you how many moles I have. So here's what I'm going to tell you. When I ask you a question, and the question is in moles, and it's asking the answer to be in moles, you jump for joy, right there. You say, yes. That's when you're going to really love the mole at this point. If I ask you in grams, okay, and I'm gonna have y'all make sure that y'all do a lot of practice problems converting back to grams so you get that. That's probably the central thing you need to understand about chemistry the whole year, okay, is converting moles to grams and grams back to moles. All right, that's the central idea of chemistry. All right, so let's see what we know. We know that we have 12.2 moles of ammonium sulfate, that's our product. How many moles do I need of ammonia to make that? Okay, so I'm going to calculate that by taking my 12.2, take the thing I know and do what with it? Put it over 1. Yeah, if we can start there, right? I'm going to put that over 1 right there, and then I'm going to relate it. So it takes 2 moles to make 1 mole of that. So here in the factor label method, just don't forget that you've got that 2 right there. Don't forget it, that it takes 2 to make 1, so therefore 2 over that, over the 1, is my representation of 1, right? And then I'm going to just pull the math through there. So now I have 24.4 moles of NH3. And that's my answer. Now, was that very difficult? Not difficult at all. I'm going to ask you another question. What about H2SO4? You should be able to tell me right now how much of that I need. Go.
6.1.
Well, it's 1 to 1. 12.2. You get it? That's why moles are. All right, do y'all have this written down? And do keep in mind that it is in your textbook if I end up going too fast. I also am recording the lecture today for Julia. Hi, Julia. She's in the snow. Yeah, so probably sledding. We got snow too, hun, so.
She actually doesn't have any snow.
No snow?
There.
No way. We built a snowman, Julia, so booyah. Yeah. My snowman's still standing.
I was like, you're not snow in Texas, you're in New Hampshire.
Did you send her pictures and say, look at that? Okay, good. Yeah. All right. Are we good? Okay. Now let's talk about limiting reactants. Okay, so if I'm going to perform an experiment and I want to get a yield, mostly, if we're talking chemistry as a practical matter, we're trying to make something. Okay, I'm trying to make something. If I'm a sunscreen seller, which I would never be, if I were, I want to make this chemical that goes in sunscreen, right? So I want to do what I need to do to get that chemical, and I want to do it in the most efficient way possible. And so sometimes what I might do is manipulate my chemical equations so that I could get it quicker, I could get more out of it. I wouldn't waste anything that was expensive, things like this. And so what we're going to look at is something called limiting reactants. Our lab next week will be experimenting with some limiting reactants. So when there's more than one reactant in a chemical equation, one of those reactants will usually run out first. Okay, think about your little volcano you made in elementary school, right? You made your volcano with your baking soda and your vinegar, and it comes bubbling out. It's awesome, and then it stops. So what do? You pour a little more vinegar in there, and it goes again, right? So what had run out in that case? The vinegar. It had run out, and I needed more. Now, can I do that indefinitely? Not really. What's going to run out eventually? The baking soda. Okay? All right, so we call that reactant, the one that runs out, the limiting reactant, because the reaction cannot continue when it runs out. Therefore, the limiting reactant limits the amount of product that can be formed. Oops, are y'all supposed to write any of that down? Okay. All right, so I like this picture right here. So let's see our reactants and our products. See all the stuff we have right here? And we have excess reactants. So if I have too many buns, too many tomatoes, and too much cheese, what was my limiting reactant in this particular equation? Meat. And who wants a burger without the meat? No. But maybe 2 slices of cheese or 2 slices of tomato. All right. So fully analyzing equations. So this is just my little reminder for you of what you're going to do when I give you a question, a problem to do. Number one, you're going to write and balance the chemical equation. Sometimes the equation will be given to you and you'll have to just balance it. Sometimes I'll just tell you what's happening. Combustion, formation, decomposition, something like that. And you have to figure out the equation and then balance it. Step 2, relate the number of moles in the substance using the stoichiometric coefficients. Those are the big numbers in front that we can mess around with all day, right? We don't play with the little numbers. We never ever do that. Calculate the number of moles and then show the math. And that is your easy problems. Okay, so how do y'all feel about balancing equations? You're pretty good at it now? Remember, just keep track of everything. You can write it all down and keep track that way. So when we get to having to convert our moles to grams here in a few minutes, remember what you'll need for that would be your periodic chart of the elements. All right, so that's important at this point. All right, so let's look at this one. If I start with 1 mole of magnesium, okay, is this balanced? Let's see if this is balanced first. Magnesium plus hydrochloric acid gives me magnesium chloride plus some hydrogen probably floating off, right? Is it balanced? Yeah. Looks good? Yeah, looks good. If I started with 1 mole of magnesium, yay, then I know that I must have 2 moles of hydrochloric acid in order to get 1 mole of magnesium chloride, right? If I use less of HCl, then that would be my limiting reactant. If I use more of HCl, so I make sure I get every last little bit of magnesium out of my sample, then magnesium would become my limiting reactant. So a balanced chemical equation provides that information needed to make a chemical reaction proceed. So here's our example, the one you're going to write down. An antacid tablet called Tums with the active ingredient calcium carbonate, CaCO3, neutralizes excess hydrochloric acid in your stomach according to the following reaction. CaCO3 plus 2HCl yields CaCl2, that's a salt, inert, H2O and CO2, and I'm guessing it's balanced because I've got my 2 in there already. My calcium looks good. Oxygen looks good. Carbon looks good. Yeah, we're balanced. Good. All right, but don't always assume just because there's 1 stoichiometric coefficient already on there, don't assume that it's balanced. Somebody might be trying to trick you. It would never be me, intentionally. I don't ever want to trick anybody. I think that's not fair, okay? All right, so here we're going to, look at this number we're using. That happens in chemistry all the time. 0.0075 moles of calcium carbonate are in a tablet, all right? How many moles of hydrochloric acid can it neutralize? And then how much of the CaCl2, H2O, and CO2 would be produced in this particular case? So what's the first thing I'm going to do?
Put that in CO3 over 1.
0.0075 moles of CaCO3 over 1. Is that what you said, Abby? Okay. So let's see. There it is. All right. Put it over 1. All right. And then I'm going to relate it to my hydrochloric acid, which has a 2. Okay. So you don't forget that 2 moles of hydrochloric acid to that 1 mole of CaCO3. So now do you see how I'm relating 2 of the reactants together? It doesn't have to be over there to the product. I can relate anything. So now I'm looking for every 1 mole of CaCO3. I need 2 moles of HCl. So I relate those together that way. There's my 2. And then I calculate the math and I get 0.015 moles of HCl. It's a breeze. That's easy. Now, what about the rest of them? Who's got it? Are you saying it? looked like you were saying it. Saying something. Mumbling. Mumbler. All right, who's got it? How many moles of CaCO3 are going to, how many moles of CaCO3? 1. Going to relate to this. How many are there? How many there? How many there? Okay. So, if I'm relating those? 1 to 1? You don't even have to do any math. They're all 0.0075. Because they're relating 1 to 1. Do you get it? See, awesome. That's great. It's just that 2 that was the only problem there, which I had to do this for right here, which brought me out to this math over here. You get it? Yeah. All right, so when you see that everything else is related to the 1, then, remember, because it was asking us how the CaCO3 relates to the rest of them. Not how the HCl relates to the rest of them, because that would be different, because it would be 2 to 1 for everything else if you were talking about the HCl. You get it? All right, so that's telling you right here how that works. And then you'd have, so you could just write those in. You don't have that math right there. You just write these answers down. Yeah? Okay? That's cool. All right. This, I have the whole long video of that thing we just talked about. I'm guessing nobody wants to watch that 7-minute video. Okay, good. All right. So now relating the products to the reactants in the chemical equation. So I've got my products, my reactants right here. A chemist wants to make ether, C4H10O. The chemist needs 134.9 moles of ether. There's my number. What is the minimum number of moles of reactants that he's going to need right there? All right, so first thing I'm going to do, 1.34.9 moles of C4H10O over 1. And I'm going to relate it to, it's this, it relates to this one with a factor of 2 there, a factor of 1 there. All right, so I have this. Here's my 2 and here's my 1. Therefore, I need 200, gosh, I'm sorry, that's so small, y'all. 269.8 moles of C2H6O. What do I need of H2SO4?
134.9.
Yeah, 134.9. Exactly. Okay. So you might be wondering, well, gosh, everything's just the same. What's it? Well, but since the molecule's different, then its grams will be vastly different. Okay. That's because moles and grams. We have to get those by looking at the molecule itself. All right. Yeah. So I didn't even put this one in, the second half of it, because it's just that number right there. That's how powerful moles are. Those moles relate. It's pretty cool stuff. In fact, it almost seems sort of impossible that it worked out so neatly and so nicely. Huh. It's almost like it's designed that way. How about that? Like a lot of scientists in the world would say, it has the appearance of design. And I would say that appearance is because it's designed that way. Thank you very much. They do admit to an appearance of design, which I find interesting. An appearance. All right, are we good? Yes? All right, here we go. Now, this becomes important if we're using something expensive. All right, here we go. A chemist wants to make silver chloride, AgCl, okay? And you get it from this Ag2CO3 right here. It turns out it's very expensive because guess what? It's got silver in it. And silver's expensive. We use silver for a lot of things, including like computers and stuff like that. A lot of electronics in our cell phones. A lot of those use silver. I'm not sure if they use it in the form of silver chloride. I'm not sure exactly what that's for. I know the old-fashioned way of making photographs, it was silver chloride. That's what made those negatives of an old photograph. So since it's expensive, we want to ensure that none of it gets left behind, none of it gets wasted, so it'd be smart to make it the limiting reactant. Do you get it? So we're going to put in excess hydrochloric acid, so much more that we know we're getting all of that silver out of there. All right, so we're going to add excess reactant. Then he should be sure to use more than 2 moles of hydrochloric acid. There you go, right? All right, so when the limiting reactant is identified, so here's another time when we're using silver. We're going to try to just get pure silver out of this. Let's say that I believe that this right here, this 2KAgC2N2 is considered silver ore. So if I'm a miner and I'm digging into the ground and I find this vein of silver and I want to actually extract the silver from it, I can do that chemically and get that silver out right here by reacting it apparently with zinc. I find that interesting. I wonder how that gets done. So a chemist adds 5.61 moles of this silver ore to excess zinc. How much pure silver can be made? All right, so we have our 5.61 moles. How does it relate? That is I'm assuming that's a balanced equation right there, which I told y'all not to assume that. But it looks good. Kind of nice when the C2N2 is C2N2 over here as well. Yeah, it looks good. All right, so we're going to take what we know, put it over 1. We're going to relate our 2 to 2, and we come up with 5.61 moles of silver. Who already had that without even doing that math? Yeah, because it was 2 to 2 or 1 to 1. Right? So we didn't have to go through this whole rigmarole, but if you struggle with the math on problems like this, go through the whole rigmarole. Prove it to yourself, okay? But I'm okay with you just telling me that you just when you see it, I'm cool with that, okay? I'm happy with that. When you see it, praise God that He's made it visible to you, okay? Sometimes we get it, sometimes we don't. Oftentimes, and I'm in the second group, I don't get it. So I have to work at it. All right. Remember, we're looking at coefficients. All right. So the big number in the front is coefficient. Now, on your midterms, now, did everybody get a chance to go figure out what your grade is? The Jupiter's working? Because it's all in there. All right. Yeah. I did write your grade down on your thing here. So, this one's yours. Do you mind handing this one back, Priscilla? Thanks. All right, so remember, because some of you did make the mistake of trying to mess with those little tiny numbers down there. Never. The only time you put a number down there is if you're figuring out an equation. Like if you're figuring out a combustion equation and you know that CO2, you're going to put that 2 down there, of course. Okay, H2O, you're going to put that down there. If something is a hydrogen, it ends up, always put that little 2 because it's a homonuclear diatomic, okay? But once you've got that part in, the only thing you can do to balance an equation is to deal with the coefficients. That's the only thing you can touch, all right? So there's an interesting phenomenon that has come about, which I find also very interesting, and a very brilliant man, a Frenchman, mais oui, came up with this. His name was Joseph Louis Gay-Lussac, Monsieur Lussac. He found out something that he had a theory that the volumes of gases correspond to the stoichiometric coefficients in a chemical equation. And so all that's saying, here he is, Monsieur Lussac, right there. And he did a lot of testing with gases, which I find fascinating. It's kind of hard to work with gases and not have some of it escape or whatever. But you remember when I told you there was going to come a time when those little parentheses with the G for gas is going to be important? This is it. All right, this is it. So remember, there's aqueous, there's liquid, there's solid, there's gas. All right, so right here we can see everything here is in a gas. So this stoichiometric coefficient right here tells me I have 3 moles of hydrogen gas plus 1 mole of nitrogen gas will yield 2 moles of NH3 gas. All right, so that's what's happening in this equation right here. What Monsieur Lussac figured out was that stoichiometric coefficient not only corresponded to moles, it also corresponded to the volume, liters, the liters of gases. In other words, for this one, I don't have to convert. I can use that stoichiometric coefficient to calculate the liters of gas I need to do a reaction, as long as I'm relating gases to gases every time. It has to all be gases. Okay, so it only works then between gas and gas. Does it make sense what I'm saying to you? You want to see an example? So the volume relationships for gases in chemical reactions now uses what is known as Gay-Lussac's law. It states that the stoichiometric coefficient in a chemical equation relate to the volumes of gases. It also still relates to the moles. Okay, it relates to the moles and the volume of the gases, the liters of gases, as well as the number of moles in the substance of the equation. And I think you have a question, what do we need to be looking for? You need to be looking for that they're gases. They must be gases. What's important? Have y'all left y'all with some blanks on your book? If those are probably OIOs, and I want you to do the OIOs on your own. Okay, so I do some of them here. Mostly I do the examples here. And I'd like you to write them in your book there. I am going to be a little more tough in grading your books in the second semester. So look through what I did I graded them, right? So look through any comments I may have made. Mostly it would have been put in a conclusion. Write a conclusion, draw me a picture, tell me what you did, that kind of thing. And so I'll be tougher on the second semester on your lab grade. I'm pretty easy on the first semester. I want to make sure you understand what I want. And what I do want is those boxes that say, oh, I used to have writing in them. So when you're doing your study at home and you look at go ahead and just write it in your book right there instead of a separate notebook or something, okay? All right, here's our example. An automobile engine burns gaseous octane, C8H18. This is a combustion reaction, all right? If the auto completely combusts 12 liters, what could I say instead of 12 liters? I could say 12 moles, right? Yes, it's going to be synonymous at this point. Of gaseous octane in excess oxygen, how many liters of CO2, that's what it's asking, how many liters of CO2 will be produced? Okay, first we have to balance it. You know right away if we're looking at a combustion reaction, it's certainly not balanced, and it's probably going to be a little bit of a messy balancing situation going on here. Mostly because we have an 18 right there, right? Yikes. So anybody want to take it on? I think it might take too long. I'm gonna tell you what it is. There's a 2 there. There's a 25 there. This is starting to look familiar. We may have done this one already, right? There is a 16 there, and then now you can guess because you have done this before. What's the last one? It's going to be 18. So look at those stoichiometric coefficients. Now do you see why the factor label method is really important for us on this one, right? Really important because we don't want to miss one of those stoichiometric coefficients. We got to make sure that gets into my fraction when I'm doing my conversion reaction going on there. All right, so do we have a balanced equation there? I don't think, I think I do. On the next slide is just going to be a still shot from the long video that we're going to skip, okay? And so it should have it on there. There it is, yeah. So here it is, 2, 25, 16, 18. So it takes 2 moles of octane to make 16 moles of CO2, right? And therefore it takes 2 liters of octane to make 16 liters of CO2. And if we lived in Europe, we would know we'd get our petrol in liters already. Here we'd have to say, well, how many gallons is that? I mean, because we're Americans and we do weird measuring. We still put our gas in our car in gallons. But everybody else in the whole wide world practically puts it in as liters. So we wouldn't even have to do any conversion at all. So we need 2 liters of octane to get, to use it up. We need 16 liters of CO2 in order to use up my 2 liters of octane. And then, what else did it ask us? How many liters of carbon dioxide are produced? Oh, right there, there it is. We're going to take our liters, relate them to each other, the 16 over 2. And we end up with 9, so I need 96 liters of CO2. That sounds like a lot to me. 96 liters. I could have said 96 moles. Liters are a little more relatable. Sorry, the car burns 12. I forgot to tell you that part, didn't I? The car burns 12 liters of that, so that's where our 12 came from. Okay? All right, there's the long video. Now we're at 8B. And the first part of 8B is going to be the fun stuff, okay? Which you will have to watch videos for this. I'm going to make you watch some videos for this. Okay, so stoichiometric applications. I'm going to be looking at mass now. Okay, so we've been talking about moles and then liters. So cool, other gases, we're happy. Thank you, Monsieur Lissac. And now we're going to be looking at mass relationships because if we're going to try to do something in the lab, we have to be able to measure it. And so we have to measure it with a gram scale. All right, so we're measuring stuff next week. We'll be measuring stuff on gram scale and using it in a reaction. Remember that stoichiometric coefficients in a chemical equation relate to the number of moles in each substance. Furthermore, we know we can determine the volume of each substance if they are gases. But how do we relate the masses? Unfortunately, we must convert to moles to figure out the relationships and then convert back to grams. All right, so I have my sad face. Okay, this is just lots of steps, that's all. And I wouldn't skip a step. I can't skip a step. So what are the steps using stoichiometry? First, you must balance the equation, obviously. 2, determine the question, and then calculate grams per mole of the named substance. Figure out what are we asking for. 3, determine the mole-to-mole relationship by what? How do we do that? Yeah, but how do we find it? Stoichiometric coefficients, right? Okay. And then determine the number of moles of other substances in the reaction, and then whatever it asks me for, convert back to grams. It's a lot of steps. Here we go. Let's roll. A chemist needs to make 100.0 grams of GaCl3. How many grams of Ga and HCl will he need? All right, so we have a number, 100 grams, all right? And then we have, look at our stoichiometric coefficients. We have a 2, we have a 6, we have a 2, we have a 3. Boy, that's a lot of coefficients. There's no ones on there at all. Okay, so we're going to watch the next video. Don't fall asleep. Okay, I don't know, is there a box for this one? So you may want to, at the very end, I'll keep the answer up there, and so you may want to just watch it. Don't write anything down, and at the end, I'll give you time to write down what you want to write down, okay? All right, because I really want you to pay attention to how we do this, because if you miss a step, then you're going to miss the whole problem. All right, here we go.
This example is your first introduction to complete stoichiometry. In this example, I'm given a chemical equation that's balanced, and I'm given a certain mass of product. And the question is, what mass of each reactant is needed to make this mass of product? This is the power of stoichiometry. Mass is something that's very easy to measure in the lab. You take the compound, you put it on a scale, you measure its mass. A chemical equation can relate the mass of the reactants to the mass of the products given the stoichiometry. So that's what we're going to show you here. All right, let's get to it. I need to figure out the mass of Ga and the mass of HCl necessary to make 100.0 grams of GaCl3. How in the world am I going to do that? Well, the first thing I have to realize is I can't do anything with a chemical equation unless the quantities I'm working with are in moles. Grams don't mean anything to a chemical equation. The chemical equation gives you the relationship between each substance in terms of moles. So when I have grams, the first thing I have to do is convert to moles. And we know how to do that. We look at the periodic chart. GaCl3 has Ga and Cl in it. Here are the entries for Ga and Cl3 on the periodic chart. I can use those entries to calculate the mass of GaCl3. 1 Ga has a mass of 69.7 AMUs. 3 Cls have a mass of 35.5 times 3 AMUs. The total then, 176.2 AMUs. That's the mass of a GaCl3 molecule in atomic mass units. That also tells us that it takes 176.2 grams of GaCl3 to make a mole.
Remember that?
So that gives us a conversion relationship between moles and grams. 1 mole of GaCl3 is equal to 176.2 grams of GaCl3. Now that I have a conversion relationship, I can convert. I take the number I know, 100.0 grams of GaCl3, I put it over 1 to make it a fraction, and then I multiply by our conversion relationship. I need to put 176.2 grams of GaCl3 on the bottom so that that unit cancels, and that puts moles of GaCl3 on the top. So when I multiply these fractions out, I get 0.5675 moles of GaCl3. Now remember why I had to do this. I'm trying to figure out how many grams of each reactant I need. But the chemical equation doesn't tell us anything in terms of grams. It only tells us something in terms of moles. I now know that I'm working with 0.5675 moles of GaCl3. That will allow me to relate to moles of Ga and moles of HCl. And that will help me solve the problem. Alright, so now that I have moles of GaCl3, I can finally look at the chemical equation. The chemical equation relates moles of one substance to moles of another. So there's a 2 in front of GaCl3. That means 2 moles of GaCl3. I want to solve for Ga first, and the number in front of Ga is 2. That means 2 moles of Ga. So that's our first relationship. 2 moles of Ga
Yay.
equal 2 moles of GaCl3.
1 to 1.
This allows me to convert from moles of GaCl3 to moles of Ga. So I take the number I've got, 0.5675 moles of GaCl3, put it over 1, multiply by the conversion relationship. I need moles of GaCl3 to cancel, so that goes on the bottom. When I multiply these fractions then, moles of GaCl3 cancel, leaving moles of Ga. So when I multiply through, I get 0.5675 moles of Ga.
We already knew it.
Now understand what I've learned here. I've learned that if I want to make 0.5675 moles of GaCl3, which is 100 grams, I need to start with 0.5675 moles of Ga. Now that's nice to know, but it's not the answer. The mean guy who wrote this problem asked you how many grams of Ga you need, not how many moles. So I've got to figure out how many grams of Ga I need. That's not hard though. If I have moles, I can get to grams by looking at the periodic chart. Here's the entry for Ga in the periodic chart. This entry tells me the mass of a Ga atom is 69.7 AMUs. That also tells me that 1 mole of Ga is the same as 69.7 grams of Ga. So now I have a conversion relationship between moles and grams, which is what I need. So I take the number I know, 0.5675 moles of Ga. I put it over 1, then I multiply by the conversion relationship. I need moles to cancel, so moles of Ga go on the bottom. And when I multiply these fractions through, moles of Ga cancel, and I'm left with 39.6 grams of Ga.
Okay. So I'm going to pause it there. Do you want to write that down? Because next we're going to go to hydrochloric acid, I think. Because it asks for both. Yeah, we need HCl next. All right, so this wasn't too bad on the mole part, right? So remember I was telling you earlier, it seems like, well, gosh, it's so easy. They're all the same thing. But look how it's way different, right? Because of what we were using, what our molecule was. So, and I don't know about you, but I could maybe skip this step right here, where I'm finding out that those are the same, 2 to 2, 1 to 1. I could skip that, but I can't skip any of it. I got to do every bit of this math myself. So now we can measure out 39.6 grams of that Ga pretty easily on a scale. So next we're going to be looking at how hydrochloric acid is related to it, I think, right? And therefore that stoichiometric relationship's not going to be quite as easy, is it? It's not the same. It's 2 and 6, right? All right, are we good? Y'all still writing? We're going to just continue with this same problem. So next week we're going to have a quiz over this module, and you'll need to bring your periodic chart of the elements, right, and calculate it.
Now think about what I was able to do here. Given 2 things, a balanced chemical equation and the mass of product I need to make, I was able to use stoichiometry to calculate the mass of reactant I needed to make that mass of product. That's how powerful stoichiometry is. Well, we're not even done yet. Stoichiometry allows us to relate the mass of one substance to the mass of any other substance in the chemical equation. So I can calculate not only the mass of Ga needed, I can calculate the mass of HCl needed. So I'm going to do that. Let me save this answer, 39.6 grams of Ga, so that we don't forget it. And so I'll put it on the bottom right-hand corner. And I'll erase the stuff having to do with Ga. And now let's start the calculation for HCl. Okay, notice I didn't erase everything. Why? Well, I still need to know the number of moles of GaCl3 that I want to make. After all, the chemical equation relates the moles of one substance to the moles of any other substance in the chemical equation. I know I need 0.5675 moles of GaCl3. Now I would like to find out how many grams of HCl it takes to make that. So, let's look at the relationship between GaCl3 and HCl. The number to the left of HCl is a 6. That means there are 6 moles of HCl in this equation. There are 2 moles of GaCl3, so the conversion relationship is 6 moles of HCl equal 2 moles of GaCl3. Now I can convert. I take what I know, 0.5675 moles of GaCl3, I put it over 1, and then I multiply by our conversion relationship. Moles of GaCl3 need to be on the bottom so that they cancel. When I multiply through, I'm left with 1.703 moles of HCl. Unfortunately, that's not the final answer because the mean guy who wrote this problem wants the answer in grams, not moles. So I've got to convert from moles of HCl to grams of HCl. So to do that, I need to look at the periodic chart. Here are the entries for H and Cl from the periodic chart. They tell us the mass of HCl. I take the mass of H, 1.01 AMUs, and add the mass of Cl, 35.5 AMUs, and the calculator tells me it's 36.51 AMUs. Unfortunately, I have to drop the 1 because I'm adding, and when you're adding, you have to look at precision. The least precise number, 35.5, goes out to 10ths place, so my answer can only go out to 10ths place. All right, so that's the mass of HCl. That tells me that 1 mole of HCl is 36.5 grams of HCl. That's our conversion relationship. So we take the moles of HCl, we put it over 1, and we multiply by the conversion relationship with moles of HCl on the bottom so that they cancel. When I multiply through, I get 62.2 grams of HCl. That's the final answer. So, given 2 pieces of information, a balanced chemical equation,
Yeah, I'm gonna start writing that part down.
and
if
the
you want-
mass
if you
of
wanna
one substance in the chemical reaction, I was able to calculate the mass of other substances in the chemical reaction. In order to make 100.0 grams of GaCl3, I need to react 39.6 grams of Ga with 62.2 grams of HCl. Now realize what I had to do this. I first had to convert the mass of what I wanted into moles, because chemical equations talk only in moles, not grams. So when I have grams of something, and I'm interested in working with a chemical equation, I immediately have to convert to moles. That will allow me to get to moles of any other substance in the chemical equation. Once I get to moles of any other substance in the chemical equation, then if I need to, I can convert back to grams. That's the general plan of a complete stoichiometry problem. You start with grams of a substance in a chemical equation. You convert to moles. Then you use the chemical equation to convert from moles of one substance to moles of another substance. Then once you have moles of the substance you're interested in, you simply convert back to grams.
Okay. How do you feel? Okay? That's the hard stuff, y'all, right there. So if you got that, and remember those steps, don't forget to go get your chart out and figure out, where do I get that number from your chart? All right, so here we go. So we have a mass. We turn it to moles, convert it to moles. We find our molar ratio with our stoichiometric coefficients. We find the mole of the unknown. We convert back to grams. Okay, easy breezy. All right, so this is a story. This is a molecule called anhydrine. And so when I was in high school, I was the intern for my science teacher. She really liked me, you know. And so she said, okay, well, I need you to make this solution for my next class that's coming up. All right, but what you're going to have to do, I have a very small amount, so I need you to convert over here because you're going to get the mass and find out how many moles it is so we can, so I had to convert it from grams to moles, then back to grams again so I could get the proper weight of the stuff that I had, so to know how much I needed to mix it with, all right, to make this solution. And so I was like, oh, it was a really challenge for me. I haven't even practically used that stoichiometric formula, right? So I'm going through there and I'm figuring it all out. I figured it out. I found it. I checked my math with her. She said, yes, your math is right. It's great, you know, excellent. So I took it and I took the stuff and I dumped it into the giant flask and I mixed it all around and I got it ready for her. And she said, did you mix that with water? And I said, well, yeah. She goes, you were supposed to mix it with acetone. So I ruined the entire thing. So the class could not proceed. So she could not do her class. And I was so proud of myself for doing my stoichiometry right. I failed to read the instructions say mix it with 1,000 liters of acetone. I just assumed water, and that was my wrong thing. So it's just stuck with me, and I felt just horrible. It was the last bit of anhydride we had in the whole school, and yeah, it was a mess. So read your instructions. That's the lesson on that one. And maybe I was being prideful. I don't know. Look at me, my stoichiometry. All right. The human body produces the energy it requires to live by burning simple sugars like glucose. C6H12O6. We breathe oxygen. This is a combustion reaction. We breathe out CO2 and H2O. Everybody should recognize that chemical equation right there. It's something you've been learning for many years in your ODA career, right? It's the one that students, when they're in any class, they put that reaction, they get a couple extra points, right, for remembering that this is the combustion reaction or the respiration reaction. So this reaction proceeds with a lot of heat. That's why we have a temperature, 98.6 degrees, which is used to power the body's motion. If the average adult human burns about 1.2 kilograms of glucose each day in excess oxygen, breathing well, how many grams of H2O are produced? Okay, so we're asking for grams. All right, so right away you go, ugh. Okay, because the first thing we know we're going to have to do is we're going to have to do some converting here. All right, so it says here pay special attentions to OYO 8.6, 8.7, and 8.8. Are there boxes in your book for that 8.6, 7, and 8? Okay, it says just pay special attention to those. All right, so but we're going to watch this question right now on video.
In this example, we're dealing with the combustion of glucose that takes place in the body. And the question is, if we start with 1.2 kilograms of glucose and burn it all, how many grams of water are produced? Well, this is a stoichiometry problem. You know it's stoichiometry because you're being asked to relate mass of one substance to mass of another substance. About the only way you can relate the amount of one substance to the amount of another substance is through stoichiometry. We have a balanced chemical equation, so we can get started. As is the case with all stoichiometry problems, we can't work with the chemical equation until we get into moles. So our first job is to take the mass of glucose and convert it into moles. Well, we immediately see a problem. The only way I know to get from mass to moles is by using grams. We don't have grams of glucose here, we have kilograms. So the first thing I have to do is convert kilograms to grams. I'm going to assume you know how to do that by now. So 1.2 kilograms converts to 1.2 times 10 to the third grams. Now I can finally get to moles of glucose. To do that, we look at the periodic chart. Here are the entries for C, H, and O. To get the mass of glucose then, we take 6 times 12.0 for the 6 carbon atoms, plus 12 times 1.01 for the 12 hydrogen atoms, plus 6 times 16.0 for the 6 oxygen atoms. When I add this together, using the rules of significant figures for addition, I get 180.1 AMUs. Now that also tells us that 1 mole of C6H12O6 is equal to 180.1 grams of C6H12O6, and now we can convert to moles. So we take the number we know, 1.2 times 10 to the third grams of C6H12O6, we put it over 1, and we multiply by the conversion relationship with grams of C6H12O6 on the bottom so that they cancel. When we multiply through, we get 6.7 moles of C6H12O6. That's the number of moles of C6H12O6 that are being burned. We can relate that to the number of moles of water being produced. This relationship comes from the chemical equation. If we look at the chemical equation, the coefficient next to C6H12O6 is blank, so that means it's 1. And the coefficient next to water is 6. So that tells us that 1 mole of C6H12O6 is equal to 6 moles of H2O. That gives us a conversion relationship. So now we convert. We take 6.7 moles of C6H12O6, we put it over 1, and then we multiply by the conversion relationship. Moles of C6H12O6 is going to go on the bottom so that they cancel. That leaves moles of H2O on the top. So when I multiply through, I get 40 moles of H2O. Now the problem is I need 2 significant figures here because 6.7 has 2 significant figures. So I'll have to express 40 as 4.0 times 10 to the 1. That's the only way I can make that 0 significant. All right, well, that's actually an answer to the question how much water is produced. 40 moles tells you how much water. Unfortunately, the mean guy who wrote this problem wants the answer in grams, not moles. So we'll have to convert from moles to grams. You should be an expert at that by now. The entries for H and O on the periodic chart are there above. H has a mass of 1.01, O has a mass of 16. So H2O has a mass of 18.0 AMUs once you account for significant figures. So that tells us that 1 mole of H2O is 18.0 grams of H2O. So now we can convert. We take the number we know, 40 moles of H2O, we put it over 1. Then we multiply by the conversion relationship. We need moles of H2O on the bottom so that they cancel. And so then when you multiply through, you get your answer, 7.2 times 10 to the 2 grams of water.
All right, there it is. Now, I'm okay with it not in scientific notation. All right, so 7,200, right? Like right up here, it's okay if you didn't put it to the 10 to the third. So we can, but look also, we can relate that same number, this one, our 6.7 moles here, to these other ones as well, right? Our 6 and our 6 here. So we already know that relationship now, because that's 6 to 6 right there. So I think it's going to be that same way as long as we go through and find our grams based on the molecule itself. All right, but this one only asked for H2O, so that's all we had to do. All right, good? There's that answer there. I just put that on there in case we needed to see that for those details. Okay. All right, so now we're going to use stoichiometry a little differently now. This is sort of at the end of the module right there, and more time is spent on it than I would prefer, but so I'm going to cover it. I really think the stuff we've talked about until this point is the key that you need to understand. But there will be questions based on this stuff we're fixing to talk about. It's just not as critically important as the previous stuff. All right. So we can use stoichiometry to determine a chemical formula of something. All right, we can figure out what it is. In other words, we can put those little tiny numbers down below once we figured out what they're supposed to be. If I have an H and an O and it went to H2O or H2O2, I can figure those things out using stoichiometry, it turns out. All right, so when a compound or molecule is decomposed, all of the elements and the atoms in the compound will be separated. Once they're separated, their mass can be measured. Using the mole concept, the mass allows us to calculate how many atoms of each element existed in the compound. Once we've counted all the atoms in the compound, we can determine what its chemical formula is. H2SO4. I always give that to you, but there's a way to figure that out using stoichiometry, okay? So, a chemist decomposes an unknown compound. The products of this decomposition are 12 grams of carbon and 4.04 grams of hydrogen. What's the chemical formula of this unknown compound? All right, so I've got my C and my H, so it's CH, CXHY, C something, H something. We don't know, but we can figure it out using this right here. It seems kind of strange, but we can. All right, so let's watch it. Another video, sorry.
In this example, we're using the results of an experiment to determine a chemical formula. A chemist takes an unknown compound and decomposes it into 12.00 grams of carbon and 4.04 grams of hydrogen. All right, those are the only elements that result from the decomposition. So this already tells us something. There are only two elements in this compound, carbon and hydrogen. So even though I don't know the chemical formula, I can represent it. I can represent it as CXHY. After all, the chemical has only carbon and hydrogen in it. There will be a certain number of carbon atoms, that's X, and a certain number of hydrogen atoms, that's Y. So that's a representation of the chemical formula. Well, that's nice, but it's far from an answer. We need to figure out what X and Y are. How are we going to do that? Well, think about this for a minute. This is a decomposition reaction. We know what a decomposition reaction does. It takes the compound and produces its elements. So in this case, CXHY decomposes into carbon, that's C, and hydrogen. Now hydrogen's a homonuclear diatomic,
H2.
so it's not H, it's H2. All right, so here's a chemical equation for this decomposition reaction. How does that help? Well, think about it. The chemist gave us grams of carbon and grams of hydrogen. I can convert those to moles. Where do moles go in a chemical equation? They're the coefficients. So if I convert grams to moles, I'll essentially get the coefficients that go with C and H2 in the products of the reaction. Let me show you how that works. The chemist's reaction produced 12.00 grams of carbon. I can convert that to moles if I look at the periodic chart. The entry for carbon on the periodic chart tells me that the mass of carbon is 12.0 AMUs. That also tells me that 1 mole of carbon is equal to 12.0 grams of carbon.
That's good.
That's our conversion relationship between grams and moles. So I take my grams of carbon, put it over 1, and multiply by the conversion relationship with grams of carbon on the bottom so that they cancel. We find out that the chemist produced 1.00 mole of carbon. All right, now we do the same thing for hydrogen. The chemist produced 4.04 grams of hydrogen. The entry on the periodic chart tells me that a hydrogen atom has a mass of 1.01. We're not dealing with hydrogen atoms in the equation, though. We're dealing with hydrogen molecules because hydrogen's a homonuclear diatomic. So the mass of H2 is 2 times 1.01, or 2.02 AMUs. That tells me that 1 mole of H2 is equal to 2.02 grams of H2.
Oh, I like that too.
That's our conversion relationship between moles and grams. So now I can convert 4.04 grams of H2 times the conversion relationship, putting grams on the bottom so that they will cancel, gives me 2.00 moles of H2. Now what does all this tell us? It tells us that when CXHY decomposes, it makes 1 mole of carbon and 2 moles of H2. Well, where do those moles go in a chemical equation? They're the stoichiometric coefficients in the chemical equation. So I can actually put them in the equation. Now remember, numbers in a chemical equation are exact, so 1.00 wouldn't make sense in a chemical equation, so I'm just going to get rid of that 0.00 and call it 1. In the same way, 2.00 wouldn't make sense in a chemical equation, so I'm going to get rid of that 0.00 and just call it 2. So in the end, the chemical equation becomes CXHY decomposes into 1C and 2 H2s.
See where we
Because
got
I produced 1 mole of C and 2 moles of H2. Now do you see how this can help us determine the chemical formula of a compound? There's only one way this equation will balance, and that's if X equals 1. I've got 1 carbon on the product side, so I can only have 1 carbon on the
What does
reactant
Y need to
side.
be?
So X must equal 1. In the same way, the only way this equation will balance is if Y equals 4. After all, I got 4 hydrogens on the product side, so I can only have 4 hydrogen on the reactant side. So in the end, the chemical formula of this compound must be CH4, because that's the only way this equation will balance. Now let me make it clear what I did not do. I did not change subscripts in this chemical equation.
because we can't do that.
I'm not allowed to do that. You can't touch subscripts in a chemical equation. However, X represented something. What I did was I found out what X represented. It represented 1. Y represented something. I figured out what it represented. It represented 4. So I did not change subscripts here. I only figured out what the subscripts represented.
All right, you get it. All right, okay. All right, so the OIOs that are on that page, you're going to do those on your own, okay? But there's going to be several of those doing that conversion thing to find out what the formula is, okay? All right, some of them are harder than the one we just did just then. All right, so this brings us back to the empirical formula that we talked about. Now, we have talked about empirical formulas before. Do you remember this? We talked about empirical formula, but we're going to talk about it again now. And then I think kind of unfairly, Anne-Marie, I think you were the only one who had the empirical formula question on the midterm. Is that right? Anybody else remember having an empirical formula question on the midterm? So for whatever reason, Anne-Marie's test was different, and she had it on there. Yeah. So we may not have covered it, so that probably wasn't fair that you got counted off for that one. So the empirical formula is a simple whole number ratio of atoms in a molecule. We only know the ratios. A molecular formula is the exact number, okay? So each type of atom in there, okay? This is a blank, I think, in your book you're supposed to be filling in. The molar mass is the mass of 1 mole of a given compound, grams of 1 mole, right? So we've just been through how we get to all that and how we manage through all that kind of thing right there. But the empirical formula is essentially doing sort of a least common denominator kind of a thing. All right, so you have several boxes on the top of your page there, or right, 3 boxes right there. So here it is.
One more, we have, there's something else.
Oh, I missed something? Molar mass, the mass of 1 mole of a given compound, is that at the top of the page? There's a blank right there, yeah? You got it in there? Okay, so we're going to be kind of working, even though we've talked about empirical formulas, we're going to work with a little more in this module right here. So right here, we have a formula for C4H12. So go ahead, write C4H12 on the left side of the first box there, and then draw an arrow to tell the empirical formula. We're going to basically reduce it down using kind of like least common denominator kind of a thing. Okay, so what would we look like? What could we do to make those numbers empirical? All right, because they're related, right? What if we divided both of them by 4? Can we do that? And so our empirical formula is going to be CH3, you see here. Now, personally, I don't understand why we have to do this. Because CH3 and C4H12 are not the same thing. So why are we doing it? I don't know why we're doing this. Unless we're going to do one of those problems in the OIOs you're doing, you're going to come back and figure out what it is. Knowing the empirical formula will give you a step up of knowing what the final formula will be. Okay, I just think it's a waste of time. Okay, N2S2O8. We're going to reduce that one down. What's that going to be?
NaS2O4.
Except for that S2, I think, can go away too.
Yeah,
NaSO4 right there. So that goes in your second little box up there. And then look at this one, K2CR2O7. Can we reduce that at all? No, that 7 messes everything up. It's already empirical. Okay, it's non-reducible, to speak in math terms. All right, so you're just going to have several questions like that in this module, and just there may be one on the quiz. I don't know. I don't write the quizzes for this class. If I did, I wouldn't put any of these on there. I'd put more of the converting grams and moles kind of a thing, because I think that's the central lesson of today's module. Okay. A compound's empirical formula is determined to be CH2O. Okay, CH2O. We know it's not its final because it's just its empirical formula. In a separate experiment, okay, the molecule's mass was determined to be 180.1 AMU. What is the compound's molecular formula? So this is another way to find out that molecular formula. All right, to go from an empirical formula to a molecular formula, we must multiply by a common factor. So the point here is we're going to try to figure out what is that common factor. All right, how can we do that? And so we're going to find our molar mass of CH2O. How did we get that? From the periodic table, right? At 1 carbon, 2 hydrogens, and 1 oxygen, and that's going to, trust me, it's 30.0 AMU or 30.0 grams, right, per mole. All right. The common factor, a mass, this is how we find it. So this is the key right here. If you're going to write something down, write this down. The common factor is the mass of the molecule divided by the mass of the empirical formula. The mass of the molecule, 180.1, divided by the empirical formula, which we just calculated to be 30.0. So really, if you just remember that little key, that little step, then you're good to go. So we'll do it. We take our 180.1 AMU divided by 30.0 AMU, we get 6. So 6 now has become our common factor. This tells us if we multiply each number in the empirical formula by 6, we will get a molecule's empirical formula, CH2O, and whose mass is 180.0, and that's going to be C6H12O6. So that's why we do it. Anybody lost?
Wait, what did we do?
So we took what we knew from experimentation, 180.1 AMU, all right? And then we found the AMU for the empirical formula by going to the periodic chart of the elements. And then to find the common factor, we divide the mass of the molecule divided by the mass of the empirical formula. So that's 180.1 divided by 30.0 gave me 6. So 6 is my common factor, so I distribute that throughout the whole empirical formula. You get it? Okay. Once again, I don't see the point of this, but it's in your book, so got to do it. All right, let's do another one. A compound's empirical formula is PO3. So what I know right off the bat, that the answer is not PO3 because it tells me it's empirical, right? Well, I don't know. We had that one that was already empirical, but they're not going to give us that trick. Okay. If its molar mass is 158 grams, yikes, what is its molecular formula? All right, so the mass of 1 mole of this compound is 158 grams. Its molar mass is 158 grams. So a mass of 1 mole of the compound is 158. That makes sense. Okay. So the molecular mass of the compound must be 158 AMU, right? Okay, so don't let... I see gram and it makes me go, but here, in this particular case, it's not a problem. Because 1 mole equals 158 gram, 1 mole equals 158 AMU. We just know that from chemistry. So find the common factors. So you're going to divide the molecular mass by the empirical mass. So that's 1, we had to find PO3. We had to find that one, the empirical mass. So the PO3, we had 31, that's P, times 3 of the 16, that's O, gives me 79. So now I'm going to divide the molecular mass by the empirical mass. 158 AMU divided by 79 AMU gives me 2. Hooray. And now what am I going to do with that 2? Distribute it. So I'm going to have P2O6. So it's not really so bad, right? Not really so bad. All right. Do you want to do the more complicated one? Yeah. It's a video.
Oh, no. How long is it?
I don't remember. A sample of brown colored gas decomposed into 2.34 grams of nitrogen and 5.34 grams of oxygen. So we know it decomposed to that. So we know we just have nitrogen and oxygen. What's the it's only asking us for the empirical formula. That's actually similar to the first one we did. Okay, so I don't know how long it is. Here we go.
In this example, we're taking the results of a chemical experiment and determining an empirical formula. Now, we've done something like this before. We look at the compound and see what it decomposed into. It decomposed into nitrogen and oxygen. That means that its chemical formula is N something O something. So we can represent that as NXOY, and we can write its decomposition reaction. NXOY decomposes
You remembered about N2
into
and O2.
nitrogen, which is a homonuclear diatomic, so that's N2, and oxygen, which is also a homonuclear diatomic, so that's O2. To determine the coefficients of those products, we're going to have to determine how many moles of each product were made. All right, well, we know there were 2.34 grams of nitrogen made. To convert to moles, we look at the periodic chart and find that the mass of nitrogen atoms are 14.0. However, we have a nitrogen molecule as the product, N2. So its mass is 28.0 AMUs. That means 1 mole of N2 is 28.0 grams of N2. So now we can convert to moles. We take the number of grams, 2.34, and multiply by the conversion relationship with grams on the bottom, so that they cancel, and moles on the top. So in the end, the chemist made 0.0836 moles of N2. Now we do the same thing with O2. The entry for O on the periodic chart says that O atoms have a mass of 16.0. We're not dealing with oxygen atoms, however. We're dealing with oxygen molecules, O2. So we have to multiply that number by 2. So the mass of oxygen molecules are 32.0 atomic mass units. That means 1 mole of O2 has a mass of 32.0 grams. So that's our conversion relationship. We take the number of grams we have, 5.34, multiply by the conversion relationship with grams on the bottom and moles on the top. That way grams cancel and leave moles. And we find that the chemist produced 0.167 moles of O2. Now these numbers aren't nearly as nice as what turned out in the last example, are they? In the last example we made 1 mole of carbon and 2 moles of hydrogen. Here we're making 0.0836 moles of nitrogen and 0.167 moles of oxygen. Okay, those numbers aren't very nice, but we'll toss them into the chemical equation anyway. The chemical equation won't be realistic yet, but we'll do something about that in a minute. So the chemical equation is NXOY decomposes into 0.0836 moles of N2 and 0.167 moles of O2. Now what we need to do is turn these numbers into integers. How can I do that? Well, there's a trick that mathematicians employ every now and again. If they need to turn a group of numbers into integers, they divide by the smallest of them, and they see what happens.
That's a trick that I did
So
not
let's
know.
take these two numbers, 0.0836 and 0.167, and divide by the smallest of them, 0.0836. When we do that, 0.0836 divided by 0.0836 is 1, and 0.167 divided by 0.0836 is 2.
Hooray.
Now, in terms of significant figures, we have three significant figures, so it's 1.00 and 2.00. But at least now we've got integers, or something close to integers. Now, just like before, 1.00 doesn't mean much in a chemical equation because the numbers are supposed to be exact, so let's get rid of the 0.00s. Now I have a pretty simple chemical equation.
Now we can figure that out.
NXOY makes N2 and 2O2. To balance this equation, X has to be 2 and Y has to be 4. Alright, that's a chemical formula, but it's not an empirical formula. This kind of experiment can only determine the empirical formula of a compound. To determine the chemical formula, we need to know something else, like the mass of the chemical involved. We don't know that in this case, so the best we can do is an empirical formula. Remember what an empirical formula is. An empirical formula is a formula that contains only the simplest whole number ratio of atoms. This formula doesn't do that because 2 and 4 have a common factor, 2. So this isn't the...
Okay, so we get that. So the only thing is that weird little math trick. So who's a mathematician in the room? Have you heard of this trick before? I don't know that trick. I'm not a mathematician. Okay, but I'm just going to trust what he's saying is true. I did notice, did y'all notice when we had these numbers, that how they related, that they were half? That was half of this one? Excuse me, where am I? Yeah, this one was half of this one. Yeah, I said, ooh, 16 and 8. I said, that's something we can work with right there. So that's why it was more complicated, because you had to put those weird numbers in there. So the fact that he put them in there and then did that division, I thought we were going to have to divide them. Yeah, so. All right, so apparently just write this down somewhere, remember it in your head. Number 6 on page 622 is a good one to do. I guess that's similar to that one. And then remember, you're going to bring your study guide and have a quiz next week and a lab next week. Okay? Are we good? Not too bad? The hardest module of the year? Not too well. It rivals with 13. 13's pretty hard too, but 8's the tough one. So, all right, I will see y'all next week.